Hello, my name is Mike Miller. I'm going to present to you a constant current power supply that was designed for Project Lab A at UMass Lowell for the fall 2017 semester. A little bit of background. The company I work for designs a variety of temperature sensors, a lot of which use RTDs or resistance temperature detectors to provide that temperature output. One test that we're often required to perform is to find out what the self-heating effect due to current flowing through the RTD is. Self-heating can cause error in the RTD's output measurement. There's usually a specification on how much of an effect that self-heating can have. In prior tests, the actual RTD voltage was measured, RTD resistance was measured, and a fixed voltage was applied across it. This worked okay, but one problem that you have is as the resistance of the RTD changes, the current will change since the voltage is held constant and not the current. So the idea was to create a device that would be capable of providing that constant current that would be independent of the load connected. So it wouldn't matter if the resistance of that RTD element changed due to that current flowing through it. There will be a constant amount of current flowing regardless of what changes may happen there. The device would obviously require facilities connecting input power, which would be provided through a DC power supply, the load, which would be the RTD, and an ammeter or a data acquisition system that would be used to provide a amperage output and to log that data throughout the test. Other requirements are that the device have selectable current ranges from 5 to 50 milliamps with a tolerance of plus or minus 0.005 milliamps. The device must be capable of driving that current through loads of at least 1 and 220 ohm RTDs, but will be designed to provide current to as high a load as possible. The device will also have a means of displaying the actual current output to the nearest milliamp. The basic system design uses a Texas Instruments LM317 voltage regulator, which is a 3-terminal device that will source the necessary current to maintain 1.25 volts across the output and adjust pins. The device will work by varying the resistance across those pins so that the current sourced will change. And as an example, for a 5 milliamp current with the 1.25 volts across it would require a resistance of 250 ohms between the output and adjust pins. So for the other ranges, that resistance will change. To provide the visual indication of the current, the voltage across a sense resistor, which is placed in series with the load, will be used. With the 5 to 50 milliamp current, a 100 ohm resistor will provide a convenient 5 volts at 50 milliamps and half a volt at 5 milliamps. A PIC microcontroller will be used to sense that voltage across the 100 ohm resistor using an A to D converter. And the PIC will also drive 2 7-segment displays and convert the ADC output to the current output and display that on the 2 displays. The first round of prototyping, the LM317, a precision 250 ohm resistor, and a 220 ohm resistor were used to simulate the RTD. These are wired onto a breadboard just to check the basic operation and that it would function as intended. The ammeter that was connected between the 220 ohm resistor and ground indicated that the current output was 4.98 milliamps, and this current remained steady for a number of hours. Once the basic functionality was confirmed, more detailed calculations were carried out. The resistance required for the variety of loads needed were calculated. You see here with R1, 250 ohm resistor for 5 milliamps, 125 for 10 milliamps, 62.5 for 20, and 25 ohms for 50 milliamps. The current and the maximum load that can be driven by at each range are shown here. And as to be expected, the load goes up as the current goes down. One thing that the prototyping showed is that a means for fine-tuning the resistance across the output and adjust pins is needed. The 4.9 milliamps that was observed instead of the 5 milliamps during the prototyping showed that having just one fixed value resistor wouldn't cut it. So a means of adjusting that resistance and therefore the current would be needed. The reason for this is that the output voltage across the output and adjust pins is not exactly 1.25 volts. It's pretty close, but it's far enough away that having a fixed value resistor in there isn't really practical. Next step was to figure out, okay, what size potentiometer would I need to place in parallel with that resistor. So using standard value resistors, the total resistance was calculated based on a potentiometer resistance that would be in parallel with R. And the standard value resistors were used such that the potentiometer setting would be about the same, and you can see that here, that they're all right around, between 750 and 800 ohms. What that does is, as one range is selected to the next, you don't have to do much adjusting of the potentiometer to get, from 5 milliamps to 10 milliamps. The 50 milliamp was a little tricky because the resistance is so low that there's not as many standard value resistors down at this range that I think the next lowest was 24 ohms, which is too low. So that one will take a little bit of adjusting, but it'll be able to provide that output regardless. Quick overview of the design. The power from the power supply is input to the LM317 and also to a 5-volt regulator, which is used to power the microcontroller and the 7-segment display. The 4 current ranges are selected with a multi-position switch and adjusted with that 1K potentiometer. The load and the ammeter connected in series with the 100 ohm resistor to sense the current. And the analog to digital converter in the PIC is connected across that 100 ohm resistor. 9 other PIC outputs are connected to the solid state, 7-segment displays, and 2 PNP transistors that will be used to switch back and forth between displays. So you see here, this is where the 30 volt input is applied. There's a switch to turn the device on and off without having to shut the power supply off. The 5-volt regulator is here with the LED to show the power status when the device is switched on with the switch. That 30 volts is also fed into the LM317 up here with those potentiometers and the range select resistors up in this area. You can see the load and the meter are connected directly in series with that, and the 100 ohm sense resistor resides down here. So you've got the load, the meter, and the 100 ohm resistor all in series to ground. You have a 1K resistor here with a 1000 picofarad cap prior to the analog input of the PIC microcontroller. The 1K prevents a significant amount of current from flowing in there for a number of reasons. One, to keep from damaging the PIC, and the other to keep from dragging the voltage down of the sense resistor too much. The 5-volt supply, you can see, is connected into the microcontroller here, and also above these, the emitters of the PNP transistors, and the 7 outputs go to the 7 displays, the 7 segments on the 2 displays, and the software that's written for the microcontroller will basically switch back and forth by turning on the output for either of these PNP transistors to turn on one digit or the other. The final build looks something like this. You've got the fine adjustment pot here, the multi-position switch here, Your provisions for connecting the load, or sorry, the input voltage here, the power supply, the ammeter or data logger here, and then the load here. You've got the power switch up here with the status LED and the display here. Okay, a quick demo of how this constant current power supply works. Got my DC supply hooked up here, set to 25 volts. Ammeter hooked up and a resistor 220 ohms to simulate the RTD that'll be used. Fire it up here. You see the rough range displayed here, the actual output here. Make some fine adjustments with the potentiometer on the front panel here to dial this into 5 milliamps. Bump that up to 10. Make some slight fine adjustments here to get up to 10. Close enough. And 20. Another quick adjustment. The 5, 10, and 20 milliamp ranges all fall within about the same potentiometer setting by design, just to avoid having to hunt around for those settings as you switch the range. The 50 milliamp takes a little bit of hunting, a few more turns of the pot, but it does get there eventually.